Hello, good evening. So I think it's time to start. Please confirm if I am audible. So,
Yes, sir. You're
okay,
audible.
thank you. In today's session, we will see push-pull converter and half bridge and full bridge converter, which is left from converter's point of view, and we will solve some problems as well based on that. So yeah, my screen is now visible. And so, what was need for push-pull converter? If you see there are already so many converters, so why do we need push-pull converter? So, Raja Sekhar, do you have any answer for that?
No, sir.
Okay. So, sorry, you were saying something?
No, sir. No.
Okay. Generally, lot of such isolated converters, they usually have positive kind of polarity. I think there is some certain noise from your side, so
Okay.
if you, yeah, thanks. So there are already certain isolated converters which works on induction principles, so that we can have infinite gain ideally, or we can have very high gain based on number of turns and all. But if you observe the supply, they only fed by the positive voltage or polarity, right? We do not see usually with negative polarity. And why that is important? Why polarity of voltages are important? So first thing is, if you apply negative polarity of voltage, so you will see that flux linkage or flux that will also be in negative direction. So, but peak to peak, if you see, that will be almost twice. And in any magnetics domain, there is nothing negative and positive. It is just the direction of that quantity has been reversed. So, uh, essentially, here also we are trying to give certain kind of supply so that the converter will operate in peak to peak with the similar kind of peak to peak value of flux as in forward or flyback, but it will require less amount of core area or less size of core. Why I am saying that? I am increasing peak to peak flux and the core area of the converter will be reduced. Why I am saying that? What is the reason behind that? So let me pose the question again. I am saying that by supplying negative polarity of voltage also, and it implies that our peak to peak flux will be doubled, or in other words, to keep the peak to peak flux same as of other isolated converters, the size of core will be reduced. So I want to know some answers from you why I am saying that, or what are the reasons behind that.
Sir.
Yeah, go ahead, please. Anything in your mind?
No, 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 sir. Your voice is break now, so I couldn't hear what you said. Can you say it again, sir?
Oh, my voice is breaking.
No, 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 no. It is okay. Problem in my side, sir.
Okay, okay. So, let me repeat the question. What I asked that for the same flux or same flux density, if I am utilizing negative polarity of voltage as well, so that we are able to utilize lower core area or lower core size compared to other isolated converters. So I want to know the reason behind that, or even if that is true, if you are not convinced with that, you can tell that no, this can't happen. So I want to just know the reason behind it. Did you get the question now, Raja? Shekhar?
Yes, sir. The the area of the core used in these converters is less.
Yeah, area of core in push-pull
Half bridge.
push-pull or even in half bridge or full bridge, which we will study in future, is lesser than other isolated converters, flyback or forward. So why is it so?
Because since we are the operating flux density actually reduces if we are
Operating flux density reduced, you are saying. Okay. Any
if
other thing?
the flux density if we are having bidirectional flux in the core,
Uh-huh.
uh, the actual peak comes down so that we are the positive peak actually comes down so that we will be having swing between negative bm and positive bm.
Okay. Yeah. You are almost there. You almost comprehended the reason behind that. So the thing is, uh, now you may mute please. Actually, today there are a lot of noise from your side.
Okay.
Yeah. So as RS stated that operating flux density reduced. So as I told that peak to peak flux will be same. So this kind of flux waveform was in other converters as well, other isolated converters. Okay. Now what we are essentially doing, we are just trying to shift it with the average. Okay, so that the average of flux density will be zero or average of flux will be zero. So now origin will be here, positive phi m will be on upper side and negative will be on lower side. So how are we achieving a lower core size? So see, your peak to peak flux is the same. Okay. So d phi by dt should not change and hence a voltage requirement. But the positive value of flux and negative value of peak flux that has been reduced by almost half. Okay. What could have been in flyback or forward. So if flux is now half, then flux density also can be half. Okay. And if flux density is half, then you can use almost half of the initial area to operate at same flux density. Okay. So let us suppose if this material has flux density of 1.8 Tesla. Okay. So if you reduce the material size, then your flux density will increase because that has to cater same amount of flux. So if peak flux is same, now flux has been reduced. So flux we know B into A, right? So if flux has reduced, then your area also can be reduced. So essentially we are reducing area by the quantity of a scaling of flux. Do you have any doubt in this?
Sir,
Yeah, go ahead, please.
sir, actually the relation is flux phi equal to flux density into area.
Yes.
If we reduce the peak flux, flux reduces and also the peak flux density reduces.
Hmm.
So the since if I write phi by b, area
Uh-huh.
equal to phi by b, then
Uh,
area remains same.
okay, so let me take what you are saying. You are saying that flux has been reduced by 5 by 2, so flux density also should be reduced by b by 2. That's what you are saying.
Yes, sir.
Yeah, see here, flux density will be dependent on how much flux lines are passing through the material in the given
Okay.
process. Okay, so that
Okay.
is flux density. So let me write separately the expression of flux density. Now see here, flux had been reduced by half. So let me replace it with 5 by 2. Now tell me, to operate at same flux density E, what I
Mhm.
should do?
So, area should be halved.
Area should be half. If we want to reduce, or no, sorry, if we want to operate at same flux density,
Yes.
right? Then we have to do area, half area. What will happen if I will use same area of core?
So use same area of core, then flux density will come down.
Flux density will come down, and what will that lead to?
Uh, Flux density come down, so the requirement of area comes down. Okay.
No, in that case, I am using the same area, whatever was initial. Let me denote by AI, right? AI and YI. So now I am operating essentially at VI by 2.
Yes, sir.
So, uh, is it this disadvantages, or there are any side effects, or there are certain advantages of operating at VI by 2? Whatever the saturation flux density of the core was initial, now I am operating it at half of that saturation level. So,
Yeah.
is it advantageous or disadvantageous? Firstly,
Yeah, advantage is core loss will come down.
okay, you are saying advantageous, of course, core loss will come down. Why? Because core loss will come down. Is that all? So now you see, it is now operating at near to the half of saturation level.
Yes, sir.
That is true that core loss will come down.
Okay.
So if the lower core loss is always desirable, why not we always try to design core materials with significantly higher core area than the required for the operation at the level of saturation? That's my next question. If you are saying that at this condition, I am using I am utilizing the core with lower core loss, then the general design practice should be to design with higher core area so that we will achieve lower core loss. But generally, it is not so.
Okay.
So, what is the reason?
Yeah, that's actually the core we are using is more than our requirement. The
Yes,
cross section of the core.
yeah. So, the one word I will tell you that will be the reason for that underutilization, right? If I have saturation flux density limit of 1.8 Tesla, then I should go up to 1.6 or 1.7. Even in certain cases, certain extreme cases, we can go up to 1.8 Tesla, but we can go up to safely 1.7 Tesla or 1.75 Tesla. Of course, that will lead to certain core losses, but we are maintaining lower area, right?
Yes.
And lower a space constraint is a major factor in many devices that we have to maintain, and especially in power electronics converters. That helps in reducing the size of all the devices. So, coming back to the topic now, underutilization. So, we were not utilizing fully. We were not able to utilize the coal at its full extent. So now, with the same output performance and same output parameters, we are able to operate it at almost with lower core area, right? So our area of or size of device will come down significantly. So that was the reason behind and that was the motivation behind going for push-pull converter. Okay, now coming back to circuit of push-pull. Okay, so again there will be transformers connected, but now we will have center tap transformers with two windings, right? And at the midpoint, it will be distributed to the circuit.
Sir,
Yeah, go ahead, please.
sir, basically you are saying that area of cross section equal to flux density by flux.
Flux
In that,
density by flux.
yeah,
No,
in
area of cross section is equal to flux by flux density.
yes, sir, sorry, flux
Uh,
by flux density. In that relation, you are
uh,
saying uh, in the forward converter and the flyback, we are
uh,
operating at 5 by B.
5 by B, yes.
Yeah, so area is higher, area of cross section of the core.
Uh,
Whereas in these converters, half bridge, full bridge, and these things, we are
uh,
operating at 5 by 2 by B by 2.
5 by 2 by, no, 5 by 2 by same B. B is same.
B. Okay.
Uh,
So
because
area is
saturation flux density, let's say 1.8
mm,
Tesla for certain material, when
mm,
we are shifting to push-pull converter, it will still be 1.8 Tesla for same material because we are utilizing same material. Until and unless material is not changed, we will not change. Or B max what till what point we can operate, that will not change.
okay. Oh.
Right? Flux can be changed and
Uh,
area can be changed. Is in your hand, but flux density is fixed for certain material.
okay. So area because of half of flux, we are operating in positive region. So A comes down.
Yeah, because to maintain the same flux density, A should
Uh,
reduce by same factor.
okay.
Okay, so yeah, it's good that you are clearing your doubt because it is related to magnetics, so we should be able to comprehend in terms of magnetics and circuits at the same time. Okay, so let me write the number of turns in P should be for both the primary windings and NS should be for both the secondary windings. Okay, and this is our VBC. Now here we will try to use certain a special kind of switches which should have the capability of single pole triple throw. So what do you mean by single pole triple throw or single pole double throw, single pole single throw? These kind of terms you have heard earlier.
Yes, sir.
So what is it?
Yes, the pole will be uh, shifting between the throws over a period of time t.
Yeah, means we can throw at any terminal the same switch is connected to one pole that will be fixed or to one node or one point that will be fixed and the other point can be connected to any of the three terminals wherever we want. So that will be known as triple through. So single pole, triple through. Okay. And here since both are connected in center tap fashion, all the transformer windings. And on secondary side, the circuit will be similar to buck converter. Okay.
Sir,
Yeah, go ahead.
this relation of area reduction in area will come down one in both the cases we should have the same material as you said.
It is. It should be ideally.
Okay. Yeah. Good. If you are
Okay.
using ferrite, the cross section of the ferrite will come down by half.
Yeah, yeah, that's correct. Okay, so this is the circuit of push-pull converter. Now you can see that one throw terminal is connected to ground. It means if that if this switch is connected to ground, it will not be connected to any of windings. So in that case, we will see what will happen. Okay. So let us start with when the switch is connected to T1. What what will happen in that case? That this same voltage will appear across this MP or primary winding, and it will be reflected to the secondary winding, and this diode D1 will start to conduct. Okay, and D2 will remain off because D2 will be in off mode, or it will be off. So that D1 will conduct, and yeah, sorry, I was disconnected. I don't know how there is unstable connection of internet here. Okay, so I hope now I am able to speak. Are you able to hear me? Am I audible?
Yes.
Okay. And the screen is also visible, right?
There is a break in your voice.
Okay, my voice is breaking. It is
Now,
fine now?
now it is okay. Yes.
Okay, okay. Thanks. So let me continue. I was saying that when T1 will be connected to the switch, or switch will be connected to that T1 node, then voltage will appear across the primary winding, and that will be reflected to the secondary, and this diode D1 will conduct, and it will operate as a conventional buck converter in that case. Okay, so now when this primary portion of primary portion of push pull converter will operate, in that case what will happen? So let me tell you, or I have that portion of graph here. Okay, so I am plotting the voltage across A1 and B1, and I have named A1 as this node.
Sir, we can put this image side by side.
That's what I am trying to do. Yeah, so I am calling A1 to this and B1 to this node, and similarly A2 to this node and B2 to this node. Now I will draw voltage across A1 and B1 when this switch is on, when it is connected to T1. Okay, so A1 to B1 will be 2Vi, right? 2Vs or 2VDC, whatever the supply we have connected, because of course, why it is coming out to be 2VDC? Why I am saying that it is 2VDC?
Across MP, sir. Across
Across
MP.
A1 and B1. I am drawing this with A1 and B1. A1 and B1.
Okay, across AM. Yeah, it is a dot convention, so coupling happens. So
Okay, yeah, that with the effect of coupling, 2VDC will come here. Because when we throw the switch by KVL, VDC will appear here, and same VDC will appear to the this let us say C, taking only C1 and C2. So from node C1 and B1, it will be reflected from the induction. So it will again VDC plus VDC. So it will become 2 VDC. Okay, so if it is happening 2 VDC, now the same voltage of this VDC and this VDC will be reflected on the secondary, and it will be VDC, and VDC by L should be the slope of the inductor current here. So let me draw the flux, since I told you whenever I am applying the positive supply, I will get uh, positive slope of flux, and whenever I am applying the negative supply or it is connected to this T2, then we will get current in negative direction or voltage in negative direction, and flux will fall down. So let me draw the flux waveform as well. So it should be something like this. Okay, so flux is,
sir,
yeah,
uh,
go ahead.
sir, voltage across the primary.
Hmm.
Uh, if we measure in the arrowhead direction,
Uh-huh.
it has to be minus VDC, right, sir?
Oh, yes, yes. From this convention, it should be. Is it right now?
Uh,
No.
yeah, sir. With this convention, bottom negative and top positive, the source, if it comes across the primary winding, it is minus
Okay.
VDC.
Minus plus plus minus. So
Yeah, bottom should be plus and top should be.
yes. minus plus plus minus. Now it is correct, right? On lower side, it will be same.
Now every dot terminal will have the same polarity.
Mm, if you apply KVL in this direction, minus VDC plus Q, so it should be V.
Yeah, that the switch is open, so KVL can be applied.
So that some voltage will appear across the switch also. So let me change the polarity here. Uh,
Sir, and also there will be change in the waveform. Is it, sir?
yeah, that I will have to do.
It will be minus 2 VDC.
So yeah, VP1 plus VP2. So in that case, should be, yeah, the polarity is same, and let me change the polarity itself. Because of this polarity, I think confusion may happen. Okay, so now I think if this kind of polarity will be there, plus VDC will appear here, and the same plus VDC will appear across this polarity. So I think it should be fine, right?
Yes, sir.
Now the rising slope will suffice.
Uh, okay.
Okay, so
But this A1 B1 if we measure it will be minus VDC only, sir.
this A1 B1 will be minus VDC only.
Minus 2
So
VDC.
so let me, okay, so minus 2 VDC. If I am saying it. So yeah, the slope will fall now. Let us start from falling slope. Okay,
Okay.
minus phi m to plus phi m, and the slope value will be vi by np, right?
Sir, it has to be plus m to plus 5 m to minus 5 m.
This plus phi and this minus phi. Its value will be vdc by np. So that should be the slope of flux. And after that, if we see the current, inductor current during this period only, it should be, because we are dealing here in terms of falling slope first. So, okay, and minus VDC should be on negative side. And inductor, the voltage across this diode will be plus VDC, and it is connected to inductor. So, inductor current will rise as usual with certain amount of average current. So,
Yeah, VDC minus V naught by L.
VDC minus V naught by L. And VDC, it should be ideally VDC into NS by NP.
Ah, okay. Yeah. So VDC into N. We can say.
huh. And this is IL leverage here. Let us forget. Okay. And since I haven't talked about falling edge, so when it will be disconnected and when both the switches will be off and it will be connected to the node 0 or O to the ground, then none of the voltage will appear across any winding. So voltage across A1 and B1 will be 0. It will go to 0 and say, let us suppose it was period of dt. It will be period of 1 minus dt. Okay. And since the voltage is 0, so flux should remain constant, right? V is equal to n d phi by dt. If voltage is 0, flux is constant. And if flux is constant, then what will happen to the load side?
Load side voltage also will be zero.
Load side voltage will be
No,
0.
sorry. No, no. Load side. Okay.
Load side.
Load side it will be minus V naught will appear across the inductor
Okay.
because the both the secondary side voltages are zero
Hmm.
since the flux is not changing.
So basically, whatever the inductor current till this point we have got, that will have to free will and it has to come to this initial value, right? IL will
Yes.
be.
Yes.
So it will have to free will across, along the circuit.
Yeah.
And to free will, it can go to the both windings. So ideally, this load current or inductor current, it will be divided in two portions, IL by 2 and IL by 2, and it will free will across both the diodes.
Mm.
So that's what is happening here. And in the next time zone, that let us suppose again dt, and at the end I will tell that its total time period is 2t, so frequency will be half. So again for dt, now what is happening? We are connecting this switch to T2, right?
Mm. Yes, sir.
So if it is connected to T2, now what will happen that this positive voltage polarity will be changed,
Positive.
and here also.
So secondary side will have.
Now D2 will conduct. So here during this period T1 was conducting. T1 and D1 was conducting. Here D1 and D2 both were conducting. Here D2 will conduct and D1 will be off, and from primary side T2 will conduct. So since voltage is now plus ADC, uh, so flux will rise,
Mm.
and the same phenomena will happen with the inductor current.
Yeah.
And when for again 1 minus dt, both the switches will be off, this voltage will be zero, and this flux will be constant, and the inductor current will sustain and it will repeat. So its overall time period is 2t and switching frequency will be f5. Right, so in this fashion it will keep going on, and now we have to think about some other graphs, how the waveform of ID1 and ID2 will look like, and how the waveform of switch 1 and switch 2 will look like. So ID1 is the same value as of IL during DT, during the first half of DT. Okay, and now it during this half, D1 is still conducting and it is carrying half of I naught, of course with ripple. So let us suppose this is certain I naught by 2.
Sir, uh, okay. Sir, we are drawing IL as having zero average.
No, no, no. Here
Okay.
IL has magnitude of IL average. I mentioned this axis is IL average.
Okay.
So this is finite.
It has a
And
minimum value. Okay.
and zero is, let me write, zero is this.
Mm.
Now I want to draw ID, ID1 and ID2. For ID1, what will happen? It will have certain finite, or it will have the same as IL, but it will come down to certain value I naught and I naught by 2, sorry, and it will have certain ripple at I naught by 2.
Reduced to half.
Huh. So that ripple will be almost half, and after that, this portion it will be zero when D1 is not conducting here, and here again D1 and D2 is conducting, and again when D1 and D2 will conduct, it will have similar waveform.
Mm.
So when both the switches are conducting, it is having the average value of I naught by 2 with certain ripple. So this is I naught by 2, and here this is IL max. IL max. I hope the graph of ID is clear.
Yes, sir.
Similarly, ID2 will be drawn with the shift of certain angle, and when D2 started conducting,
D2 started connecting second half. Okay. We can.
in third square block, let me show you. D2 here it is also conducting, but its waveform is
Half.
whatever it was in sharing mode. When it is
Yeah.
conducting in sharing mode,
Mm.
so it will look like something like this. And again it will conduct in that sharing mode. will be 0 for another dt period, or 1 minus dt. It is dt. Yeah, it is dt period. So this is the waveform of IDT. Now we will deal with IS1, switch 1 voltage, or switch 1 current waveform. So what kind of current it will have? Switch 1, it is
Switch one.
first of all, for how much period it is conducting?
For switch is conducting for one half.
One quarter, let's say, or we can
Yeah,
call it
yeah,
DT,
yeah.
because DT period only switch 1 is conducting, right?
One quarter of time period.
And it will have the same magnitude as of IL in secondary, but it will be multiplied with turns ratio. So N into IL, we can say that IL into NS by NP. That will be primary current. Okay, so let me then. So IS will have this shape of current, and it will not conduct for any of other three blocks till the time 2t, or till until the whole cycle is completed. And similarly, IS2 will be there, and its peak value is IP. IP is IL into NS by NP.
IL peak.
Yeah, IL. So IP N into IL peak. Okay, so it is all about current of switches and diodes. So now we will talk about voltage blocking capability, how much it will block. So when this switch 1 is conducting, or T1 is conducting, so it will see VDC and one more voltage of VDC. So here also this VDC will be there, and the voltage whatever the switch will see to block it will come to VDC at the instant when uh, one switch is conducting. Let's say if T1 is conducting, if T1 conducts, then switching capability of, or the whatever the voltage that will appear across switch T2, that will be 2 VDC. Right? So the rating of switches should be almost twice of input voltage that we have to design with. So I hope it should be
Sir,
clear. Yeah.
sir, in the circuit,
Mhm.
if we connect the pole to T1,
Mhm.
uh, across the primary we are getting plus minus VDC. Oh,
Mhm.
sorry, minus plus. Yeah. Okay, okay, sir. We are getting the magnitude of 2 VDC.
Yes, yes. The magnitude of 2 VDC we will get either in minus or plus. Okay, so it is fine, I guess. Now, what about the current rating of primary side switches? So it should be the current rating of primary side switches.
N times IL average plus del IL by 2.
Yeah, means n times IL max basically, right?
Ah,
And n is nothing but
turns
NS
it.
per turn. So this much is the current rating of the switch, primary side switch, and voltage rating we have already told that it should be 2V.
Sir,
Hmm.
here we are making the flux to move from negative to positive.
Hmm.
Uh,
Yeah.
how we are realizing that flux change? How, which currents are supporting when the flux is negative, when it is increasing to positive?
Flux is negative means flux is flowing in opposite direction, whatever
Uh,
it was, whatever in whatever direction it was flowing earlier, right?
okay.
So current will be similar, current will be same, that will not change. Just that, yeah, current will be fine. Just that the direction of flux will be reversed. So if you carefully observe the circuit, what
Mm.
you will be able to see. So when here if flux is flowing in certain this direction,
Uh,
now the flux during the negative portion or during the other half, you will see the flux is flowing in this direction. That's all. So essentially, we are changing only the direction of flux, not currents and all. The currents and voltages will change when we change the switching condition. So you see here, earlier it was flowing VDC by NP when this switch, main switch is conducting or T1 is conducting, right?
mm. Sir,
So, huh,
when we are connecting to T1,
mhm.
the current is flowing in anti-clockwise direction
The current is flowing in anti-clockwise direction, right?
in the primary top.
Yeah, yeah,
Similarly, when you connect it to T2, the current will flow in clockwise direction. Connected to
yes,
T2, that is
yes,
after the half time,
uh-huh,
when first Q1 will contact, first the top switch will contact, so the current will flow in anti-clockwise direction in the top transformer.
yeah,
Uh, and then both the switches are off, so current is zero.
huh,
Again, when again the bottom switch will be on, now the current will be flowing in clockwise in the bottom.
hmm,
Again, when both the switches are on, current is zero.
yeah, yeah. Okay, so basically the slope of the flux that is changing and it is varying from plus pi m to minus pi m by the fact that voltage polarity is changing from plus VDC to minus VDC. Earlier it was only 0 to VDC. Right. Whenever we were going from VDC to 0, then our flux was reducing till the 0 value. Now here we are changing it from VDC or 0 to minus VDC. Then our flux is going from 0 to minus 5. So it will be more clear in half bridge and full bridge if certain clarification is required. One point I wanted to discuss, these kind of circuits has certain flux walking problem. So what is flux walking problem? You will have some assignment based problems also that is based on flux walking. So do you have any idea what is flux walking?
That is, it is basically the flux is moving towards the saturation
Yeah, because of unequal distribution of voltage or unequal
switches.
drop of voltage across the switches. Yeah.
switches. Yeah.
So that will lead to, certain, nothing but VDD, right? So it will keep integrating and it will saturate towards saturation level. And it is avoided with a series capacitor that will be connected in the circuit, right? So let us see half bridge and full bridge converters as well. Okay, so
Sir,
uh-huh.
uh, sir, in this converter, when both the switches are off,
Hmm.
both the switches in the primary is off, so
Hmm.
no current is flowing through the primary winding. The current to
Yes.
the primary winding is zero.
Hmm.
Whereas at the same time, current through the secondary winding is also
Hmm.
uh, it is distributing between equally between the top and bottom.
Yes.
So with the polarity of dots we have,
Hmm.
the flux in the core will cancel each other because one, at the bottom winding the flux is entering into the dot,
Hmm.
whereas in the top the current is leaving the dot.
Yes. Yes.
So the flux produced by both the currents will be cancelling each other.
Cancelled. Yes.
So the net flux on the core at that instant when D1 and D2 are conducting will be zero.
Zero.
But sir, in the waveform it is not reflecting.
Okay, so basically that flux change will be zero, right? Not instantaneous value of flux. The change in flux should be zero, right?
Mm, okay.
See,
Sir,
uh,
if the change in flux, so this constant flux, sure, we need to have some constant current somewhere.
for constant flux you are saying?
Yes, sir. If at the second quarter,
Uh-huh.
the flux is constant, negative constant flux is there.
Yes, yes.
So
So see, we we have uh, brought it to minus 5 level, right? Now we are disconnecting it. So it should have certain place to discharge, right?
okay.
This is kind of see it as a magnetizing current. So it should get discharged to some circuit or certain lossy component. But it is just disconnected. It is not going anywhere.
Mm. Yeah, that is only that is taking over by the secondary current.
Yeah. So from primary side, flux is the same. But since you are seeing on the secondary side, if certain increment will happen, then only we can say that yeah, it is affecting primary side flux or whatever total flux is there. So essentially, total current that is flowing, earlier it was flowing only I in a winding, in a single winding, right? Earlier it
Yes.
was only IL.
Ah,
Now this I when we have disconnected the switch and it is connected to ground, now what is happening? This same IL is flowing in two different directions, right? Let me denote it. So if it is flowing in two different directions, the net flux change because of that current is zero. But whatever is there, that will be approximately same. Whatever there was earlier, the flux linkage.
okay.
You got the point?
Yes, sir. But mm,
Mhm. Go ahead.
okay. No, but without the current, the flux can't change. Stay at that value. Okay.
Without the current. Okay, so you are saying that in which current is not responsible for changing the flux?
No, no. That's what my question is, sir. Because both the primary windings have no current here.
Hmm.
Secondary winding current also is equally distributing, and the fluxes are cancelling each other.
Yes, yes.
So the net flux. So the the net flux in the core is zero
Uh-huh.
when D1 and D2 are not when both the switches are off. That
Mm-hmm.
is at the second quarter. But
Mm-hmm.
still, we are even though the flux seems to be zero, but we are drawing the negative 5 m. Uh, I don't know, but this flux has to be supported by some current from
So
some
you
winding.
are saying that this flux should go to zero value.
Yes, sir. If this is the, according to my understanding, it has to be zero. But
When it is open, it should go to zero. That should be the slope of flux. That's what you are saying.
mm, yeah, yes, sir. But
By
no, I'm not
uh,
saying this flux it should go to zero. But
no, no. By what you are saying, by your
mm,
logic, uh,
mm,
just forget whatever is there in the standard books and all. By your logic, you are saying that it should go in this manner.
yes, sir.
Yeah. So you see, what will happen if flux fits in this
I'm
manner?
sir. I'm not sure about the manner in which it goes to zero,
Uh-huh.
but it has to be zero at that
Yeah,
interval.
by any means it is going to zero, right? It means that flux is increasing. If you are having
Ah,
this kind of slope, it means flux is increasing.
yeah.
And it means it should have certain supply applied to the windings,
Mm,
right?
yeah.
But that is not the case. So if
Mm,
no supply is connected to the winding, it
mm,
means flux will be at the same level what it was at the initial.
mm.
So
Okay.
if you do the reverse engineering also, you will get the same logic. So
Mm. Okay, sir.
just think over it.
Uh,
Okay then, so let us solve some problem.
okay.
So a push-pull converter is given in this problem, and its parameters I am writing. Vs is 30 volt, and Np by Ns is equal to 2. Duty ratio is zero point 0.3, and inductance value is zero point 0.5 millihenry. That filter inductance, and load resistance is 6 ohm. Capacitor is 50 microfarad, and frequency is equal to 10 kilohertz. Now we have to find out the V naught, maximum and minimum value of inductor current, and output ripple voltage on that.
Yeah, there.
Okay. So you try on your. I am taking 2 minutes break, and we will be back with the solution.
Okay, sir.
दे दे काहीतरी ते खाली
Yeah, so I'm back now, so we can proceed to solve this problem.
Sir,
Yeah, go ahead.
this turns ratio has to be 2, right? NS by NP.
Here NP by NS is given to.
Okay, sir, but we can't use step down transformers. Is it we can use, sir?
Why not?
Why not?
Because we have to, this N has to be high to boost the voltage at the output, to increase the range of
Not
voltage.
not necessary.
Yeah, who is asking to boost the voltage? It is not a boost converter.
No, no, not boost. I'm saying the output voltage that we have, because it is 2N into Vi into D,
Uh-huh,
the output voltage is equal to.
uh-huh.
Okay, so if you take Ns by Np equal to 2, then we'll get higher voltage then. But this
Higher
is
vo higher voltage than supply voltage you are saying?
no, no, not supply voltage. Higher voltage than if you take Ns by Np equal to sorry, if you take Ns by Np equal to 2, we'll get higher voltage than if you take Np by Ns equal to 2. But both are okay, is it, sir?
Anything you can use.
Okay.
Can be used as buck or boost or any. So if you use, let me use volt second balance. So when D1 is forward biased, okay, so it has some voltage that is we when let me write. I hope circuit is well known. So just recall the secondary side of circuit. It is similar to buck converter. Okay. So when D1 is on, VLX is Vs into Ns by Np minus V naught. Okay. And when D2 is on, or when switch 2 is closed, this is when switch 1 is closed, right? And when switch 2 is closed, again the same value of voltage will appear, switch 1 and switch 2. But when both switches are off, then the voltage across inductor VLX equal to minus V naught. Okay. So
Sir,
what? Huh.
you are taking diode drop 0.
Yeah, I am taking diode drop 0 because diode drop is not mentioned in the problem. That's
Acha.
okay. So it this expression is similar to the conventional buck converter, just that we have Vs into Ns by Np instead of Vs only. So if we apply the volt second balance, what we will get V naught by Vs is equal to 2 into Vs in okay. Sorry.
Sir, if you consider diode drop,
Huh.
this Vs into Ns by Np will be of some reduced value, right? That thing only will change.
Yeah, of course. This whatever gain you are achieving in ideal switches, that will be reduced.
Yeah, yeah. No, no, the change will be only in this parameter. Vs into Ns by Np will reduce.
Yes.
No,
No,
VLX
no, no.
is equal to Vs into Ns by Np minus Vd minus V0.
Yeah, yeah. Okay, okay.
Yeah, in when
Yeah, that
all
will
the
reduce.
switches are
Okay.
on. And here it will be D into Ns by Np into 2. Okay, so that will come. Why 2 is additionally coming?
because of two windings.
Um, I would say because of we are using twice the time period of conventional buck converter.
Twice. The
So
frequency is double.
frequency is half actually, time period is double.
Time period is double.
Yes. So because of that, we will get this kind of voltage, and NS by NP is coming because of transfer of course. And when you try to compute ripple voltage del V naught by V naught, and del V naught was in conventional buck converter, if you see, that was del Q by C, and del I into 2 dt, or let us say, so this is entire time period. So it will have del I by half into del I by 8 if I shift it to 0 level. Okay. So when I shift it to 0 level, then we have ripple of half into del I by 2 into T by
T by 2, T by 4. Huh?
T by 4. Yes. Here T by 4 will come divided by C. And del I will be uh, sorry. And when I compute del I, so VL equal to L del IL by dt, and here it will be d by 2, right? So del IL when it was on, sorry, when it was off, then it was minus V naught divided by L into 2 minus 2 minus, let us suppose one whole time period is 2t minus d, or 1 minus 2d, we can say 1 minus 2d into t, so that will go as f. So okay, so I have written 1 minus 2d, that is time for v naught or minus v naught during off. So is there any doubt why is it 1 minus 2d? Because see, one time period is considered as 1, right? Then inductor current is having twice the value of V naught or minus V naught, because the switch is turned off for 2 times in a time period. So this turn off period is twice in a whole cycle. So whole cycle we are considering it as a 1, and duty ratio is twice. So that's why 1 minus 2d I am saying that is the total off time of the switch. When both switches are off, that time is 1 minus 2d. Is there any confusion in this?
This is off time. Okay.
This is off time.
Okay.
Okay. So basically we got V naught into F by 1 minus 2D. Oh, sorry. Del IL is nothing but 1 minus 2D into V naught. Okay. It will go here. 2D into V naught divided by FL, and del V naught is equal to 4 to the 8 to the 16. So 16C will be multiplied here. 16FLC or 1 minus 2D. And again, ripple will have the frequency that is half, right? So 1, 2 factor will again come in denominator. So it will become 1 minus 2D divided by 16F square. Sorry, 32F square. Okay. So see, every time whenever you have put in conventional buck converter as if, here you have to replace it with f by 2, and total d or off time you have considered 1 minus d there. Here we have to consider it 1 minus 2d.
Sir,
And yeah, please.
here the first equation you have written delta L is equal to minus V0. Sub very
No,
first. That is
there is
not correct, na?
where
The first equation. This is delta IL is equal to minus V0 F divided by
that is wrong. Yes,
that is no, that is not correct.
that is
So
not.
what you are flown after that, this is okay. Delta L
Uh,
is 1 minus 2D V0 FL. It's okay.
because I wrote 1 minus 2d in denominator, it should be in numerator.
Numerator
Yes.
V0 by L into delta dt, whatever.
Yes. Yes. So basically del V naught by V naught is
Mm.
this 1 minus 2d divided by 32 f square. So for the problem was given here that we compute, okay, we did not compute. So let me compute V naught by Vs, or that V naught value. So V naught value will be Vs into Ns by Np into D, and it is 30 into 2 into zero point 0.3. So it is 9 volt. Is it?
It is two times now, sir.
Huh, 2 times. That's why it become 9 volt. Sorry, it is 2, and Ns by Np is half, right? Because Np by Ns is given 2, so Ns by Np will be half. So it will be 30 into zero point 0.3 only. So
Mm,
these factors will be cancelled.
okay.
So since input was 30, output is 9 volts. So it is not mandatory to boost always. So it can be reduced as well. And reduced with the factor of more than 2. So generally in conventional converters we cannot go with gain of more than 2, but here reduction has been happened with the factor more than 2 or even more than thrice. Now del IL we need to compute, right? So del IL will be
Sir,
for yeah.
similarly in buck converter,
Mhm.
how much is the maximum output voltage we can get? for input of 1 volt, suppose.
For isolated or non-isolated?
Non-isolated buck.
Non-isolated, maximum you can go up to factor of 2. So if you have duty ratio D, you can go up to your supply is 1 volt, you told.
Yes, sir, for a buck converter.
For 1 volt, you can not go beyond zero point 0.5 also.
Okay. If it is an isolated, sir.
In isolated, you can go whatever you want because
Uh,
here isolation and turns ratio you can manipulate.
uh,
So you can go easily up to factor 10, means zero point 0.1 or even lesser factor, because that will not make any sense if you go to certain that much low value. But yeah, you can go.
Okay. Sir,
Yeah, please.
if input voltage in buck converter is 10 volt, then we can we go up to 9 volt?
In which
Buck
convention?
converter,
Isolated,
non-isolated.
non-isolated. You can go up to 9 volt.
But
9 volt, 9 volt is nothing but
point 0.9 T
point 0.9. So that you can easily be below D of zero point 0.5 means the ratio should not be less than 2 generally.
ratio should not be less than 2.
Vs by V naught should not be greater than 2. That's what I am trying to say. In buck.
Vs upon V naught should be greater than.
yeah, this
Should not
basic. Yeah,
should
V
not
naught by Vs should be half. Will
hmm,
not be.
V naught by Vs should not be less than zero point 0.5. Should not.
Why?
There is limitations and some derivations are also given in the book. You will see that if you go above that kind of gain, then certain damage with the circuit has been observed. So the reasons are given in the book if you see.
Means duty cycle less than point 0.5 we should not do.
It will create certain issue, certain severe issue. And I am not able to recall exact issue, but that is there.
We have to
But
operate more than zero point 0.5 to zero point 0.9.
more 0.5 to 0.9. So that's why we shifted to isolated. Actually,
And
the
synchronous buck,
synchronous buck can go.
synchronous buck can go less than zero point 0.5.
Actually, the reason behind was might be drop in the circuits. So
Drop in.
drop because in practical circuits you will have certain drops, and when you try to solve certain numericals with practical circuit, means certain resistance series with the filter inductance and ESR equivalent series resistance with the capacitor, then you will see that significant drops are there and your efficiency is very poor. So that's what I'm able to recall, that efficiency becomes very poor as you move towards 2, the value, the gain ratio of 2.
But if there are buck converters with working or input voltage is 24, output voltage is 12, input voltage is 24, output voltage is 5 volt or like that.
If there is 5 volt, then it should be isolated. But research are going on, so maybe someone has cracked or someone might have designed with certain specific things. Or so, have you seen in some practical data or somewhere?
Yes, I have simulated that circuits, but I have not practically tested the circuit. They which
Oh,
are making from 12 volt to 5 volt, 12 volt, 24 volt to 12 volt, 12 volt to 3 volt or like that.
oh, so please verify because before making it, because and if you are simulating it, have you considered all the series resistances and all?
There are losses. The efficiency is not that good. Efficiency is
Uh,
better in point 0.5 to point 0.9 region. That is true.
yeah, yeah, efficiency will be severely
They
poor.
were severely poor, but it is going to work.
Because principle is of course same, it will work. It is nothing like it won't work, but you have to trade off with efficiency.
But in synchronous buck, it is definitely workable. The efficiency is a very good actually.
Okay, so
Synchronous
in
buck,
yeah,
like
because in synchronous bug, the switches will diodes will be in parallel, I guess. No,
yes, yes.
so their drop will be reduced by half. Yeah. So yeah, and certain modification people always tries every time. So uh, I will not be surprised if someone will come up with conventional buck converter and with a very good efficiency and duty ratio with less than zero point 0.5.
Point 0.5. Not,
It can
not
happen, yeah.
it can happen. Yes, it can happen.
Okay, so coming back to the problem we were solving. So we are required to compute IL max and IL min. For that purpose, we will need the ripple current del IL. It will be V naught into 1 minus
2D
2D into
divided.
Lx divided by F by D, right? So essentially, so, uh,
We have to take only FS, no, sir,
uh, at the
because we have taken consideration of 2D already.
hmm, hmm. So I guess no here. Let us talk in terms of time first, then it will be more easy because I want to simplify it, otherwise we will be confused. So
Yes.
2D will be in one time period, right? The off time period is 1 minus 2D into T, whatever the time period is.
Time period.
Means T minus 2D into T. So this is the off period and duty ratio we are calling when the switches are off. So sorry, when the switches are on. So when we go with Lx, because Lx will be here on the left hand side, Lx into L into del IL is equal to V naught into 1 minus 2D into T. Yeah, now it is fine. So del IL we can write V naught into 1 minus 2D divided by F. Okay, so V naught was 9 volt and D is zero point 0.3, 8.3, and it will become zero point 0.7, 1 minus zero point 0.6. Frequency is given 10 kilohertz
100 microsecond.
and L is 0.5 milliampere. So it will be 9 into zero point 0.4 divided by 5. So it will come out to be 1.8 ampere. Mm, yeah, no,
0.72, sir.
0.72. Okay. It is 0.72 ampere and IL average is nothing but I naught average and I naught average is V naught by R. V naught we have calculated 9 volt and R is given 6 ohm. 9 volt by 6 ohm, that will be 1.5 ampere. So IL max would be 1.5 plus del IL by 2, so 0.36, so 1.86 ampere, and IL mean would be 1.5 minus 0.36, and that will be 1.14, I believe. And for last part, ripple in output voltage, that we have computed the expression as equal to 1 minus 2d divided by 32 f square LC, and it will be nothing but 1 minus zero point 0.6 divided by 32 into 10 kilohertz, so 10 raised to power 4 into 2, so 10 raised to power 8. L and C is L is 0.5 millihenry and C is 50 microfarad. So if we compute it, I think you will get 0.005. So ripple is nothing but 0.5% of output voltage. So is there any question in this? Okay, so we will move ahead with half bridge and full bridge quickly. So let me discuss half bridge first. So half bridge circuit will be something like uh, primary winding. It will have, and dot will be connected to same output. Its secondary side will be similar to the push-pull converter. NS and NS, and center tap transformer will be there on the secondary side. Again, primary side will have certain switch with single pole and double throw. Okay, so winding, the same winding is connected to a single pole and double throw kind of supply. So let us say VI. This is the switch here connected to node 1, and when it will connected to ground, it will have certain other value. So when it is connected to VI, okay, now the VDC or DC, that will see VI by 2, right? And when this switch will be connected to ground, it will see minus VI by 2. So the thing is that we have to fluctuate between VI by 2 to minus VI by 2, and the similar voltage will appear across this winding, similar to DC link capacitor, and that Vi by 2 will rise the flux, and the same voltage will be reflected to the secondary winding. So let me draw the equivalent circuit of primary. Let me just copy it and edit. So how does it look like when it is connected to switch 1 only? So equivalent circuit, let me draw. So it is connected to Vi, and so the flux will flow from Vi to this minus Vi minus Vi by 2 will be the effective voltage that will appear here. And on secondary side, this Vi by 2 will be reflected into Ns by Np. Np is the turns ratio of primary. And let me bring back the graph. Voila, okay, so when Vi by 2 is applied, the flux will rise from positive to negative. Phi m minus phi m flux. Okay, and when uh, this is not connected to any switch, so let us suppose when it is connected to ground only, then let me show you the circuit here. So what will happen when it is connected to ground, and when it is on, so essentially what will happen, this Vi by 2 will become minus Vi by 2 when it will be connected to the negative side, or Why? Because I have copied diagram, so let me paste it. So both the DC link capacitors will have same polarity of VDC by 2, VDC by 2, right? Since the total supply is VDC and it is distributed with DC link capacitors. And now if you see the voltage here, that will be minus VDC by 2. And during this period, the flux will die down or flux will reduce. Basically, what I want to say. And there will be one instant also when the switch is not connected to anything. And in that case, the flux will be constant. So we are trying to maintain the same operating regions as of push-pull converter. Okay, but with the intention behind using half bridge converter is to have lower voltage blocking requirement of the switches. Okay, so it will be similar, but for the given power rating, device should have low voltage standing capability or almost half of the voltage standing capability of the push-pull converter. So that's why people look forward to half bridge converter and full bridge converter. So yeah, so when voltage is zero, it means switch is not connected to anywhere. So voltage will be zero and flux will be constant. And when voltage is connected to the second or ground terminal here, in second case, this this case, then VDC by minus VDC by 2 will be the voltage, and again zero value. So it will reduce to minus plus 5M to minus 5M, and again it will be constant. And the rest other waveforms like inductor currents and voltages will be similar. This will should be the inductor current waveform. Okay, and similar, all other waveforms are similar to the push pull. Just that we will see that voltage blocking capability of switch and diode. That's the only difference between push pull and half bridge. So if you see the voltage blocking capability, if you apply the KVL across the switch of the circuit, so you will see it will be maximum VI when this switch is conducting, and ideally we place like dual kind of circuit on input, that is for, if you see, that is kind of circuit that we will have with a primary winding. Okay, so and they are all connected to supply, right? So this kind of bridge circuits will be there, and for blocking of voltage, what we will see, that is half, right? And all are connected to In full, I think this is the topology for full bridge. In half bridge, only one leg will be there. So, and they are all being supplied from the single voltage source, that is nothing but Vs. So here Vs by 2 and Vs by 2 will be distributed among the capacitors, and this will be dot NP. So whatever you will see the voltage when any of the switch is off, it will have the voltage blocking capability Vs. So if certain voltage is appearing at NP winding, so you will see the voltage blocking capability will be reduced to Vs. Okay, so that waveform, let me complete with voltage waveforms. So VSP1, uh, let us assume when switch 1 was conducting, so VS1, okay. So when switch 1 was conducting, voltage is 0 for this period, okay. And when switch 2 and switch 1 both are off, then it will have Vi by 2. And when switch 2 is conducting, it means switch 1 is off and it will have voltage of Vi or VDC. And again, when both the switches are off, it will have voltage VDC, and it will keep repeating. And similarly, it will this kind of voltage will be for VS2. Okay, when VS2 will be conducting, voltage will be 0, means here, and the maximum when switch 2 is off. So this is the waveform of VS2, and it will vary from. Okay, and its voltage ratio, if you see V naught by Vs, that will be changed, and it will have, if you apply the volt second balance, okay, so it will be V naught is equal to Ns by Np into D. That will be the ratio. If you apply volt second balance on the inductor side, you will see that it is half of the push pull converter. Okay, is there any question on this? I think I was audible, right?
Yes, sir. Yes, sir.
Okay, okay, okay. Just wanted to confirm. Yeah,
But,
so is there any
so,
question?
sir, here the advantage is compared to the reduction in the core dimension, uh, the switch rating also is reduced.
Yeah, along with that core size, switch rating is
Mm.
also reduced. So this was all. Let me give you a problem and we'll try to solve it. Okay.
Sir,
Go ahead.
no, have you last class we there is there if there is any tool to visualize the skin effect on the conductor?
Actually, I searched for that and I couldn't
Okay,
find out any appropriate tool.
okay.
Did you find anything?
No, sir. Those things I don't know.
those will be mostly visible in simulation software also.
Hmm. What kind of, sir?
Uh, like FEMM software, do you know? Finite element.
Okay.
So FEMM software, you can there easily, very easy design. There might be some tutorials on YouTube also for
Okay.
FEMM transformer code design.
Mm.
So there you
Oh,
can design and simulate a transformer, just a square or three type of transformer. There you will be able to visualize all the leakages and all the winding and some, all kind of characteristics, how it is, how flux does not flow uniformly, why some fluxes deviate to air surroundings, and what happens to the corner of the loop. So you will be able to visualize proper flux density distribution there.
oh. Is it an online tool or we can how
Yeah,
to?
it is open source free tool. So you can download just 8 MB file, 8
Okay.
MB software file is there. And
Okay.
you install it. It is very easy to install and you just start working on that. So it is
Oh,
kind of drawing. You
okay.
can draw certain lines and you can assign some materials of core, whatever core you want to design,
Hmm.
and it will have some materials or some, no, most of the materials, most of the lattice materials. It will
Hmm.
allow you to assign in itself and you can start simulating.
Oh, if you assign the material, the flux density, everything will be automatically taken.
Yeah, yeah, because if you have certain material, then the
Mm-hmm.
flux density level of that material is assigned and its
Mm-hmm.
pH curve will be given. So
Oh,
if you open that material, you can see that at how much coercive force or at how much electric field intensity, what is the value of flux density. So till how much electric field intensity you can go.
okay. Magnetic
So
field.
that,
Okay.
uh,
Mm.
magnetic field intensity, sorry.
Okay.
Yeah. So how much value of Ni you can put so that it will be within the range of our magnetic flux density saturation region
Mm.
with the given size of core.
Okay. So this is called FEM, FEM,
Yeah. FEMM.
FEMM.
Yes.
Okay.
FEMM.
Okay.
Software is what is name of software, sir?
FEMM. Let me write in the chat box as well.
IPMM for magnetic design.
Yeah, yeah. You can do electrostatic design as well. So, but mostly people do FEMM. Let me show you. So this is the FEMM, like finite element method magnetics.
Okay.
And you just go to the download and you will be able to download and you will see.
Mhm.
So I have installed, I guess. So this kind of interface will be there and you can open certain magnetic problem, electrostatic problem or any problem. So you will enter
Mhm.
magnetic problem and you will start drawing in this interface any lines or so basically transformer design will consist of some set of lines. You just design it appropriately and you will then you will be asked to model the materials and you model it and you run it, it will work.
Sir, that that the current flow problem is used can be used for skin effect. Is it? Yeah.
Current
You right clicked it. In that drop down, it is showing another form of
current
current
flow
flow.
problem. Okay,
Yeah.
so actually I exited, but for current flow problem it won't be there because current flow is related to something else.
Okay.
Basic because we need magnetostatics problem, right? Just a moment.
No, we need current distribution inside the material.
Uh,
Sir, if
but
you
that
want to see the skin effect, he has to
mhm.
use the time harmonic of FEMM, not the magnetostatic.
Okay, so you are saying that you cannot analyze frequency terms in this software.
Time harmonic, in time harmonic.
In time harmonics means frequency, right?
Not in the magnetostatics.
Yeah, that is a limitation with this FEMM because this is
Yes,
open source software. So
yes, sir.
that harmonics analysis you cannot do.
No, sir. He's saying some option of time harmonic through which we can analyze the visualize the skin effect. I think that is what he is trying to say.
Sorry, could you please repeat that? What
No,
you
sir.
said?
There is another option in this FEMM available, which is called time harmonic, through which we can analyze the skin effect. That is what I think he is trying
No,
to
no,
say. No.
uh, no. Actually, he is trying to say that this software is limited to a static problem
Okay. Okay. Mhm.
because this is an open source software. So not that much development has been done, but still you can analyze many things.
Mm.
Some paid softwares are there by EMWorks as well. EMWorks I told you.
Actually,
ANSYS Maxwell is good. Yeah, go ahead, please.
sir, yeah, for bulk parameter calculation, one can use the skin depth formula.
Hmm.
Skin depth is equal to square root of 2 by
2 by omega
omega
sigma mu.
sigma mu, and then that area reduction that will reflect in an increase in resistance and decrease in inductance.
Yeah, but he wanted to see that how it is distributed in conductor. That he want to see visually. So
Okay, okay,
that's why I said.
okay.
So if you get that ANSYS Electronics desktop student version, I think you may get if you have certain ID card, then you can
Okay.
download that ANSYS Electronics desktop for the student, and
Okay.
in that software you can do anything.
Okay.
Okay.
Okay, sir.
Okay then. So I am ending up this lesson with this last one problem that I want to pose. So the problem is based on half this circuit. Okay, switching frequency is given 50 kilohertz, D is zero point 0.4, and load power is given 48 watt. Turns ratio N, that is NS by NP, is 5, and DC link voltage is given 12 volt, and inductance is 10 millihenry, and inductor current ripple is del IL by I naught is 10%. Okay. So you need to compute voltage, of course, at output, peak current of primary switch, okay, and voltage developed across the switch means voltage blocking capability of the switch, average current of secondary diode, and RMS current of secondary diode of diode, and PIV of diodes, and yeah, that's all. So that's all you can try on yourself, and you can compare with push-pull converter. Okay, so that's all for today, and that's all from this course also because this was last week. And thank you very much to all of you for joining and consistently raising the questions and maintaining the enthusiasm for the course. So I wish you all the very best for the exam and for future as well.
Thank you, sir.
Thank you very much.
Thank you so
Thank you
much
very much.
thank you for handling the class regularly for us, and we are very fortunate that we have you as our uh, instructor.
Really, I am really grateful to have such a kind words. Thank you very much.
Thank you,
And
sir, for a very great experience that we had.
Thank you. Thanks a lot. Thanks a lot. That means a lot.
All the best to your PhD, sir.
Thank you. Thanks for
All the
that
best,
as
sir.
well. Thank you.
Thank you.
Thank you.
Bye, sir. Good night, sir.
Bye.
Bye.
Bye. Good night. Good night, everyone.
Good night.